All right, so we now know the spring constant. We have enough information here to try to put some stuff together. We are assuming an ideal spring, so the spring is massless. When we do a lab, we can't make that assumption because any spring that we have here has mass. But we'll take that into account and we'll go through an example like that before we're done today. So if I'm looking at an equation here, that one right there seems appropriate. So what's A?
5 meters.
Nope.
No.
Sorry?
Is it 10 meters?
I said one more time?
2.
Yes, it is. It's how far it stretches from equilibrium, the amplitude. This is,
Okay.
so it's going to oscillate back and forth around this point right here. So my amplitude is 2 meters because of that. Not because of this, unfortunately, I used the same number there. Omega. I'm just working through. We've got A, we now need to do omega and phi. How do we find omega?
You just do the square root of 24.5 because that's you have to divide the spring constant of 24.5 by the 2 meters that it traveled.
What formula are you using here?
The square root of K divided by M.
And what is M?
Meters.
No. Yeah.
The math.
Yes,
Oh,
it's mass.
sorry.
M for mass. So we're dealing with this 4 kilogram right here. So it's the square root of K over the mass, which is the square root of 24.5 divided by 4, which is 6.15, and then square root that.
2.47.
$6.15 is not right. 6.125, right? So 2.47 units?
Oh,
38%.
Yep. And phi, our phase shift.
Two.
How'd you get that?
2 meters.
Yeah, but that's the amplitude.
Oh,
Three, right?
You said 3?
Yes.
Why 3?
It's the layer of the spring.
All right, so let's think about this. It's not 3. So we're plugging into this equation right here. So at what point are we starting our clock? When does the problem begin?
It's the equilibrium.
It starts at equilibrium?
Yes.
Okay. Didn't have to be, but all right. So when time is equal to 0 seconds, your displacement is equal to 0 meters. That's what Gong has said. So plugging into here, that means if I'm plugging into it, I have 0 equals my amplitude times the cosine of 2.47 times 0 plus phi.
It'd be just 2 cosine 5.
All right, so this is equal to 2 cosine of phi is equal to 0. We're solving for phi. Now what?
Wait, no, it'd be 2 cosine.
5, 0.
said phi is 0?
No, phi is pi over 2.
Yes. So divide both sides by 2 so we get isolate the trig function. And now, so phi would be the arc cosine. We have to get rid of the cosine, so we do the opposite of it. So the arc cosine of 0, which is pi over 2. So given the way we started this out, this becomes so we are describing the position, this x of t is equal to 2 meters times the cosine of 2.7447 radians per second times plus pi over 2. That is the equation to describe the motion of it. If you had started time when it was out here, then phi would have been 0. Because cosine starts out at a maximum. There's another assumption that has been made here. Primarily when we said not acceleration, the amplitude is 2 meters, we did establish something.
There's no friction.
True, that is true. If there had been friction, then this would have been an equation that is dependent upon time. We will mercifully ignore friction. But we're dealing with a vector here. This is a hint. We're dealing with a vector.
With assumption that the m value is positive.
Yeah, so we established the positive direction. We established that way is positive. I guess that's 0 and then positive over here. All right, so we have our position. So how about velocity versus time? What is my velocity equation?
Negative amplitude, so negative 2 times omega. Oh wait, negative 2 sine.
So you're ignoring the omega this time?
Oh wait, negative 2 meters times 2.47 rads per second.
All right, so
Radians per second.
that's 4.94. And then sine, as you said.
Yeah, multiplied by 2.47 radians per second times time plus pi over 2.
Two things. One, it's not sine times this, it's sine of this.
Oh,
It's just-
sine of.
It's the language. And what are the units of this 4.94?
Radians.
Radian meters per second.
Oh,
Otherwise known as?
newtons.
No,
Meters per second?
what'd you say?
Meters per second?
Yeah, just meters per
Oh.
second.
Oh, okay.
Oh, that's right, radians is like a pseudo unit.
Yeah. Generally, you put it in when it's convenient trying to communicate something. If you said radian meters per second, someone would go, what, there's an angle involved? It's not technically wrong, but it might be confusing to the uninitiated. The people not cool enough to be taking physics.
Rejoice.
What was that last thing?
I said rejoice, because we're
Oh,
talking physics.
absolutely. All right, and what is my equation for the acceleration?
It'll be negative 2 meters times, times 2.47 squared.
All right, so negative
negative 12.25 meters per second. Would it be squared?
Would it?
That's good.
Oh,
Yeah, I don't know I'm not sure about the units, but I know it would be cosine of,
Alright, so we might come back to that, cosine.
2.47. That's meters per second or radian?
That's a radian.
Oh, radians per second plus pi over 2.
Ooh, you lost something in that. I suspect you would have written it down correctly, but the way you just said it, you lost something.
the T.
Yeah.
Oh,
So let me just point out an error I've seen way too many times. I curl my T's just so that it differentiates from a plus sign, and I curl my I's and J's just in opposite directions. I've seen people, when they write their T's, just do the classic, no serifs, no flair to them, just the basic cross. And then they have a plus sign, and then as they're rewriting it, they basically, that T somehow becomes a plus sign, and so it becomes positive, positive, and then suddenly they just drop one of them. So the T, I've seen disappear way too many times. Just please don't forget, there's a T in there.
that's actually a good idea what you had, so I'm gonna try to see if I can try to do that.
All right, and is 12.25 right?
See here.
12.2. Oh, you got just 12.2.
12.2?
Yeah, so it's close, very close.
Yeah, negative 12.2 as well.
All right. Now back to the units here. What are the units of 12.2?
I do think it's meters per second squared.
All right, so let's think about that, because there didn't seem to be a whole lot of confidence in that. When you take the cosine of an angle, what are the units?
It's a ratio, right? It's where like if it's in degrees, the degrees would cancel out. Or no, I'm wrong.
Part of what you said was right, and part of what you said was
Yeah.
wrong, so.
It's not a ratio of angle to angle, it's a ratio of angle to side.
It's a ratio of sides.
Yes, that's what I meant.
Okay. So therefore, what are the units? When you take the cosine of an angle, what are the units?
There are none.
Correct. So therefore, the units of this right here would be whatever the units of your coefficient are.
Oh.
So since this is position, this better be meters. Since that's a velocity, the units better be meters per second, and acceleration better be meters per second squared.
Yeah, I kinda just realized a second into that, I was like, wait, acceleration is always meters per second squared.
In SI units, yes. All right, so we've got that. At what time does this mass reach, what time is this mass here? Now, the way we have it set up, when we start the clock, this mass is moving to the right at that moment. Let's see, actually, is that right? Times 0. Well, given the way we have it set up, which way is the mass going when we start the clock? And Aaron, why do you say that?
So, because that's what we established.
We established that way was positive.
Oh.
We didn't
Well,
necessarily
usually we
establish.
associate to the right with positive. That's,
Yeah, but is time starting when you pull the mass to the right, or is it when you let go of it?
Time started when it was going through equilibrium. That's what Kong had established. That's why we have a phase shift in there.
I think the time is 0. We started at the displacement is 2 meters.
When time is 0, say it again?
Time is 0 and displacement is 2 meter.
When time is 0, this whole thing is equal to 0.
Yes.
What is this equal to when time is 0?
It'd be 0.
No.
'Cause if it- oh,
Pi over 2?
Nope.
It is negative 4.94 meters.
Yep.
oh,
When time is 0, this term becomes 0, and we're left with the sign of pi over 2.
1.
So the velocity, so when time is equal to 0, it's actually traveling to the left. If time is equal to 0. All right, so at what time is the object here? We start the clock when the thing is moving that way, so the thing has to go down and then back over to here and then back to there. How would you figure out the time when it's here?
You would find when the velocity is equal to 0. One of them.
Um,
Because there's gonna be,
Okay. So let's find out when the velocity is equal to 0, see what that gets us. So we say that middle equation, 0 equals negative 4.94 times the sine of 2.47 t plus pi over 2. That's gonna go away because we'll just divide both sides by it. So we want to know when the sine of 2.47 t plus pi over 2 equals 0. And when does that occur?
2.47 t equal negative pi over 2.
All right, so with 2.4, so I'm gonna put it in the intermediate step, plus pi over 2, when that equals 0, because sine of 0 is 0. So, and then the step that Kong had mentioned.
Negative.
what happened to that sign? I'm sorry, I missed it.
We want to find out when is the sine of this equal to 0.
Oh, okay,
And if this whole thing is equal to 0, then the sine is equal to 0.
okay.
Negative pi over 2 divided by.
Oh. All right, so negative pi over 2 over 2.47.
Yeah.
And what do you get?
1 second.
Negative 0.6.
That'd be
Oh.
63.
6.3 seconds. So this happens before the problem starts, or before at least we started timing.
It happened in the past.
yeah,
Yeah.
exactly. Easy.
Now, it is possible that the problem was going on for a while, we just didn't start the stopwatch until a certain point, but let's assume that the problem starts at time is equal to 0. All right, so what's another solution that's gonna perhaps give us a positive time? When else is the sine equal to 0?
What, just 3 pi over 2?
Acceleration 0.
Yeah, he said when acceleration is equal to 0.
Yes.
That's. Yeah.
The velocity is not 0 when acceleration is 0. Turns out velocity is going to be positive or negative 4.94 meters per second when acceleration is 0. Think about a unit circle.
Yeah, it's, didn't somebody say it's when it's 3 pi over 2? When 2.47 t plus pi over 2 equals 3 pi over 2.
Now 3 pi over 2 sine is equal to negative 1.
It was 2 pi. Wait, no, that's,
Okay, 2 pi is a solution.
Yeah.
It's not the
One
next
pi.
solution. So we got two different things here. We got when when 2.47 t plus pi over 2 equals 2 pi, that is a solution. As a matter of fact, it's going to answer the question we need. However, you did skip one of the solutions. So 2.47 t is equal to 3 pi over 2. And so t equals 3 pi over 2 over 2.47, which is about 1.9.
yeah, it's 1.9.
What solution did you skip though?
When it's equal to pi.
Pi, yeah, that's the other one.
Okay.
Because unit circle with the 0 and 180 degrees or 0 and pi, that's when the sign is equal to 0. So 2.47 t plus pi over 2 equals pi. 2.47 t equals pi over 2, and t equals, should be positive 0.63 seconds. All right, so 1.9 seconds is when the object is here, given the conventions that have been set up. Yeah, I believe I did misspeak earlier. When we established to the right is positive, that was actually basically independent of the problem that I set up. Yeah, there's no problem with setting to the right positive, it's just that was not preordained given the way other things happened. What is the period?
Period. C2.
The period is 2 pi over omega,
All right.
and 2 pi over 2.47. And is equal 2.54.
2.54?
Yes.
Seconds.
So as this thing is oscillating back and forth, think about an object that oscillates back and forth. We'll do it horizontally. The time it takes to get from here to here is the period. How much time does it take to get to the halfway point?
1.2, wait, no.
No, in this case,
1.22, wait, no.
no, not 2.2,
1.27.
2.7.
Yeah, I'm doing.
So if this is 0, this is 2.54, this is 1.27 seconds. Actually, I want to do this slightly differently. Because we started this in the middle. So that's the basic gist right there. So this point right here is 0. It gets to the halfway point at 1.27 seconds, and it gets back to where it started at 2.54 seconds. How much time would it take to get to here?
Half of 1.29.
That's a 7 there.
Oh, 7.
So 0.63 seconds. And then how long would it take to get to there?
One point 90.
Hey, that's the answer that we got over there. So we went through, the really nice thing about this is that for most of the questions that you get, there's more than one way of getting the answer. It's also a disadvantage if you sort of mix the methods in your head and try to do a little bit of, plan A and a little bit of plan B and sort of combine them. That sometimes leads to trouble. But there is more than one way of getting to the exact same solution. All right, questions to hear? There is another way of getting some of this stuff, and let's sort of proceed into that. Oh, just as a side note, I guess last Wednesday we had free food. I became somewhat uncomfortable with the dropping of the masks in order to eat. So if it does it again, if you get free food again, it's sort of keep it for after class. If you want to eat with camaraderie, you can find camaraderie outside of the room. Yeah, find that 10 months into a pandemic, I'm starting to go, oh, I'm just so tired, and I need to be I need to maintain some vigilance. Probably not the paranoia that I had 10 months ago, but at least stay vigilant. And I was saying yesterday, I was getting free food again, and he said, "You got the boys today?" And then I realized he meant you guys.
No.
So he was thinking about you.
It's looking out.
Yeah. And I was trying to remember what today's food is. Today's spaghetti? No, chicken nuggets today. Of course, at some point, the Winston-Salem school system might go, well, they really don't need as much food as they've been getting, so.
Well, that's why we gotta keep eating it.
Yeah. While you can.
Yeah. Said he woke up with a migraine today, so he's not coming.
Doesn't drive like 15 minutes to get here. Now I've got like 8 minutes.
When is the acceleration maximum? For the thing oscillating back and forth, when is the acceleration at a maximum? Think Hooke's law.
When the displacement is at a maximum.
Okay, and the problem that I just had up on the board and erased, what was the maximum displacement?
5 meters, well, 2 meters.
2 meters.
Yeah.
All right, and my spring constant again, because I actually forgot, was that, I've forgotten.
Well, it was 24.5.
It was, what again?
24.5,
Oh, that's right.
newtons
Okay,
per
thank you.
meter.
And did you say the unit?
Newtons per meter.
Okay. All right, so that's my spring constant right there. When I'm at a maximum, the force being applied would have been K delta X. I guess technically negative since I have the vector symbols in there. The magnitude of the force is 24.5 times 2, or 49 newtons. And that's equal to the mass times acceleration, which is equal to 4 times A. Because again, in the horizontal oscillation problem, it was 4 kilograms. And so my acceleration is 49 divided by 4.
It's 12.25.
Thank you. Excellent.
12.25
Units,
meters per second squared.
which was the coefficient of our acceleration problem. So another way of finding the acceleration. Now let's do a maximum speed. A second way. And this brings in energy.
Ooh.
Flashback to the energy chapters.
Right.
What are the 2 types of energy that we care about in this course?
Potential and kinetic.
Those are the 2, right. K for kinetic, U for potential energy. I assume it's Southend or whoever you had to use capital U for potential, or did they use PE?
I think it was you.
I think it was you. Yeah.
All right, I'm using U for this. So this is potential energy. Work. What is work?
Force applied over a distance.
The essence is there. Let's see if we can narrow that down a little bit better.
K divided by time.
What K? Oh,
Uh,
kinetic energy?
Yeah, kinetic energy.
Oh, no.
Is it force times distance?
Better word than what you had before, but still a little bit off.
Yeah. Force over just,
That's what I
No,
said.
no, it's closer to that.
Oh,
All right,
oh.
so the reason why force times distance is not sufficient. If I throw this marker in the air, think about after it's left my hand. Goes up and down. Let's just assume it goes up 3/4 of a meter, and so the whole distance it traveled was 1.5 meters. What force was acting on it while it was in the air?
Force of gravity.
Okay. So the work done by the force of gravity, though, is not whatever the weight of this thing is times 1.5 meters.
The
Is it-
external force times the distance.
is
Not
it
distance.
Displacement.
Displacement.
Yes, displacement.
Yes.
So work is force times displacement. So while it was going up, the gravitational force was doing negative work, and when it was coming down, it was doing positive work, and ultimately, no work at all was done. Now, you've done the business calculus, pre-calculus, the
Applied calculus.
applied calculus.
Yeah.
Did you do antiderivatives?
yeah,
A little bit.
yeah,
Okay, you're familiar with the integral sign?
yeah,
Yeah, the curve.
The big S.
Yes.
That's the summation.
Now, the reason why I bring that up, for usually in the first semester course, this is perfectly fine. That works for almost everything. However, we're now dealing with a force that's not constant. So this is true if force is constant. So if force is constant. However, for a spring, the force is not constant. The force, it starts out with no force acting on it, and the more it stretches, the greater the force is. And so force is directly proportional to the displacement, but it's not the same thing. And so we have to sort of, it's the integral of force dot dx. That's the more formal way of writing it. Now, integrals, when we do derivatives, derivative is the slope. Integrals is the area underneath. So if I had a force versus displacement